Hello, welcome to our first reading quiz for BC Calculus. In this case, it's our integration by substitution. In December, in the fall semester, we dealt with situations where we were trying to find antiderivatives. And in those cases, many of the antiderivatives were pretty easy, but now we come up to some more challenging antiderivatives. What do we do in some certain situations that are undoing tricky cases where we applied tricky derivative rules? Sometimes antiderivatives are tough. We learned some pretty simple ones in the first semester, but now it's time to look on and see some that are some challenges. And as we will see, the antiderivative of a composition will involve what's called a substitution. So here we're going to look at compositions and what to do with those. And this is the process that will undo the chain rule. So, with this process, first things first, we need to figure out what our composition is. Well, what is our inside function? So we start with an example here where we've got the integral of 2x cosine of x squared dx. And our first job is to figure out, are there any inside functions? And as you can see here, with the cosine function, it doesn't have a normal input. It's got x squared. All right, so if we were thinking backwards, if we were to take the derivative of something that had an inside function of x squared, for example, sine of x squared, our derivative would be cosine of x squared, because we're taking the derivative of the outside function, times the derivative of the inside part, which is the derivative of x squared, or 2x. Altogether, we can see that the derivative of sine of x squared would be 2x cosine of x squared, because of the chain rule. So with this in mind, it would make sense that we would just integrate 2x cosine of x squared dx to get sine of x squared plus c. Well, it was really nice, Mr. Smith, that you went ahead and gave us the answer, but how do we actually figure out what the answer is, not knowing that, not having an antiderivative in mind? How would we do that? We try to notice inside functions. In this case, we can see that the cosine function has a different input, particularly x squared. So in this case, with this knowledge, what we could do is we could substitute u equal to x squared. That's our inside function here. Informally, this gives us a really nasty integral, because if we were to put u in for x squared, we would get 2x cosine of u dx. It's kind of a problem because we've got u's and x's involved in there. Okay, so what do? We need to take care of that 2x dx part. Well, in order to make all the u's match, what we're going to do is we need to have something involving a du. That will complete our integral. In this case, since we notice that u is equal to x squared, if we take the derivative with respect to x, we would get du dx is equal to 2x. And moving that dx over to the other side would mean that we've got du is equal to 2x dx. So notice now how we've taken care of everything. We can now write the whole integral in terms of u. We've got cosine of u, that was our first step, and then we've got a du, which takes care of the 2x dx. The whole point of substitution is to make your integral easier to work with. You can ask yourself, can we integrate our new integral easily? If you can't, then your substitution hasn't done you any good. In this case, the answer is yes, we can integrate our new integral pretty easily. The integral of cosine of u du would just be sine of u plus c. All right, and we can substitute that u back in and get sine of x squared plus c. As with any antiderivative, you should always ask yourself, can I take the derivative of our new antiderivative and have it match the integrand? In this case, the derivative of sine of x squared is 2x cosine of x squared, and so we're successful. Let's try another one. You really have to practice this. And sometimes it takes a while to see certain tricks, and you really have to be a professional with the amount of antiderivatives that you know. The more antiderivatives that you know from the stuff that we did in the fall semester, the better off you'll be here. And you've got to make sure you're looking for an inside function. So let's take a look at this example here. The integral of 4x minus 1 to the 5th dx. If you remember from pre-calculus, we are trying to spot a composition here. In this case, we're raising something to the 5th power. The something is going to be our inside function, and that's going to be what we make our u. Make your u equal to 4x minus 1. And it's really helpful usually to make it the entire inside function, especially in cases where you have a constant, because when you take the derivative of that constant, that is going to go away, all right? And it will often match what you've got inside of your integral. In this case, the derivative du dx would be 4, and du would be equal to 4 dx. So notice what happens when we try to substitute. We get u to the 5th dx. Now we only need to get rid of that dx part and make it into something involving a du. But the problem is when we took the derivative, we got du is equal to 4 dx. Well, what can we do? Divide by 4. We can fix that and write du over 4 is equal to dx. And when we put everything in, we get u to the 5th du over 4 as our integrand. In other words, 1/4 times the integral of u to the 5th du, which is equal to u to the 6th over 24 plus c. And now we can substitute our 4x minus 1 back in for u. We noticed our inside function. That's the key. Here's a tricky one. Sometimes you got to be a little creative about your inside function. So our example is dx over square root of 1 minus 4x squared. And the idea is, I don't know, it looks like we've got a 1 minus 4x squared as an inside function, but the problem is when we take the derivative, we're going to get a negative 8x. And that's not going to match the dx that we need singularly at the top here. This is a situation where we've got something that looks like that arc sine derivative, if you remember from way back when we did inverse trig derivatives. In fact, if we kind of rearrange things a little bit, we can rewrite this as dx over square root of 1 minus 2x in parentheses squared. In other words, it looks exactly like what we did with that derivative of arc sine. Dx over square root of 1 minus something squared. The something is what we're going to make u. So let's make u equal to 2x. If that's the case, then we notice that du is going to be equal to 2 dx. I skipped a step there, but after a while you'll start to see how to do it faster, which would mean that dx is equal to du over 2. If we substitute everything in terms of u, we get du over 2 over the square root of 1 minus u squared. And now we can apply our arc sine rule for finding an antiderivative. We get 1/2 arc sine of u plus c, which would then lead us to 1/2 arc sine of 2x plus c. Again, take the derivative in your head, and when you do that, you notice, okay, the 2 is going to cancel out in our denominator, and when we check the chain rule here. And so we're just left with our original integrand. So you've been thinking, wow, this is pretty easy. What happens when I have to deal with definite integrals? So here's an example. The integral from x goes to 0 to 2 of x squared times the square root of x cubed plus 1 dx. Well, just like with the dx's and transferring those into du's, whenever we see a limit, x equals 0 in this case, and x is equal to 2, we have to make those limits into u. So we could take two approaches. We can deal with the limits now, or we could deal with them later. Let's start with the now approach. No procrastinating here. So based on the principles from other slides, we look for an inside function. We got a square root. It looks like there's something inside that square root, so a good candidate would be u is equal to x cubed plus 1. Hey, that works out nice, because then du is equal to 3x squared dx, which would mean du over 3 is equal to x squared dx. In that case, we can then plug in du over 3 for dx times x squared, and then we got the square root of u. We got a problem though. Can you see it? X is equal to 0 is our lower limit, x is equal to 2 is our upper limit. We need everything in terms of u. Luckily, we've created an equation that relates x and u. It's that u is equal to x cubed plus 1. And we can use that to figure out what our limits are in terms of u. When x is equal to 0, u is equal to 0 cubed plus 1, which is 1. And when x is equal to 2, we plug 2 into our equation, and we get u is equal to 9. And now we can proceed like we would any other problem. we do the integral from 0 equals 1 to 0, or to, excuse me, from u is equal to 1 to u is equal to 9 times 1/3 of the square root of u du. That antiderivative is 2/3 u to the 3/2, which runs from 0 equals 1 to 0 equals to u equals 1 to u equals 9, and this works out to 52/9 when you work that out. So a second way that we could have done this is not even bothering with the limits until we're done finding the antiderivative. So what we would find here is an indefinite integral. With the same procedure, make u equal to x cubed plus 1. Du would then be 3x squared dx, which would mean du over 3 is x squared dx. And when we go through and substitute, we don't worry about the limits at all on our integral. So when we do that, we get 1/3 times the integral of square root of u du. The antiderivative would be 2/9 u to the 3/2 plus c. And our antiderivative altogether would be 2/9 x cubed plus 1 to the 3/2 plus c. Once we got everything in terms of x, we can go back and plug in our x limits, going from 0 to 2, and in that case we would get 52/9. You can see more details about that in the reading. So finally, some hints for substitutions. This can sometimes be a challenging section because you have to test out certain things, and some things work and some things don't. You also really have to be familiar with all the different antiderivatives that we've seen in the last couple of months. But there are a couple of hints to employ. First, find an inside function. If you got something inside of a square root or a trig function, make that inside part your u. If you see that the derivative of one part of an integrand is also within that integrand, make that function your u. So, if I could scroll back for a little bit here, if you see that very first part here where we're finding the integral of x squared times the square root of x cubed plus 1 dx, the derivative of x cubed plus 1 is something involving an x squared. Wait, we got an x squared in our integrand. It matched nicely. Don't forget to make sure your limits match the variable that you're using. So if you convert everything in terms of u, use u as your limits. Otherwise, you're going to get confused about what your upper and lower limit is of a definite integral.